By now you can build a real assistant. It reasons, it calls tools, it chains them together to get a whole job done. So you hand it a real multi-step one. Watch all my subscriptions, and 3 days before any of them renews, send me a reminder. You run it once and it works perfectly. So you trust it and you walk away. And a few weeks later it quietly fails. It reminds you about one subscription the day after it already charged you. You go back and look, and here is the maddening part. Every single step it took looks completely reasonable on its own. Nothing crashed. There is no bug to find. So here is the question that actually matters, and it is not the one everyone asks. The question is not, how smart is this thing? It is this: how long a job can you hand it and trust it to finish on its own? Because that length, it turns out, is a real measurable number. And the reason it is so much shorter than you would hope is one of the most important ideas in all of AI. To see why, go back to what an agent actually is. From last time, it is a loop. It reasons, it calls a tool, it reads the result, and it goes again, around and around. A quick demo is 1 or 2 times around, but a real job is not. It is 10, 20, 50 trips around that loop. And here is the one thing we have to be honest about. Each trip is not perfect. On any given step, it might pick the wrong tool or the right tool with a slightly wrong number. Most of the time, it is fine. So let us be generous and say each single step works 90% of the time. 90%. That is an A you would call a person that reliable. So watch what happens when we send 100 of these agents to do a 10-step task. At every step, 90% survive and 10% quietly go wrong and drop out. Watch the survivors thin. By the end, out of 100 agents, only about 35 finish the whole thing correctly. Not because any step was bad. Every step was a solid 90%. The failure is in the length. Demis Hassabis, who runs Google DeepMind, put it perfectly. A tiny error per step compounds like compound interest until the whole answer is unlikely to be right. Reliability does not add across steps. It multiplies. And multiplying numbers below 1 is brutal. And it is actually worse than that clean number for a reason we saw last time. The steps are chained. The output of one step becomes the input to the next. So when the agent gets something wrong at, say, step 3, it does not stop. It does not even know it was wrong. It takes that wrong value, treats it as a solid fact, and confidently builds step 4 on top of it. Then step 5 on top of that. One bad value back at step 3 silently poisons every step that comes after it. And the agent's own mistakes become the context it keeps reading, so a confused agent tends to stay confused. By the end, it hands you a beautifully reasoned, completely wrong answer, with no idea anything went sideways. This is why agent failures feel so strange and so confident. It is not random noise at the end. It is one early crack carried all the way through. There is a second reason it gets worse, and almost no one talks about it. We said each step is 90% reliable, but that number is not even fixed. It quietly drops as the task goes on. Here is why. Everything the agent has done so far, every step, every tool result, piles up in its context, the text it has to read through before each new step. And the more text you give a model, the worse it gets at using it. This is real, and it is measured. In a study across 18 of the top models in 2025, every single one got less reliable as the input grew, even on trivially easy questions, and long before they ran out of room. There is even a name for the most famous version of it: lost in the middle. A model reads the beginning and the end of a long context well, and gets foggy about everything in between. So a huge context window does not mean a huge usable memory. The longer your agent runs, the more it has to carry, and the weaker each step quietly becomes. The chain gets longer, and every link gets weaker at the same time. But here is the deepest reason of all, and it is the one that ties everything together. Think about why compounding is so deadly here and not somewhere else. Picture a game of chess. An engine can play 1,000 moves and never drift, because at every single move, the rules of the board tell it exactly what is legal and exactly what just happened. It has a map and constant feedback. Now picture your agent out in the real world. There are no rules of the board. When it takes a wrong turn, nothing tells it. There is no signal that says you just made a mistake, and so it cannot reliably correct itself. In fact, when you simply ask a model to check its own work, with nothing external to compare against, it often does not improve. Sometimes it gets worse, confidently rewriting a right answer into a wrong one. Today's reasoning models are trained to check themselves as they think, and that genuinely helps. What does not work is simply bolting a now review yourself step onto a model that was never trained for it. So picture what we are really asking it to do. It is like handing someone one set of directions and asking them to drive across an entire country. No map, no road signs, and no way to stop and ask if they are still on the right road. A few turns in, one small mistake, and they just keep driving confidently, getting further and further from where they meant to be. That is a long horizon agent, compounding errors with no way to feel that it is going wrong. So let us put a real number on it. Researchers at a lab called METR measured exactly this. For each model, they found its time horizon, the length of task measured by how long a skilled human takes that the model can finish at a given success rate. And the result is two things at once. First, the hopeful part. That horizon has been doubling fast, lately about every 4 to 7 months, and if anything it has been speeding up. The length of job you can hand an AI really is growing fast. But now the honest part, and this is the one that actually matters. The horizon depends enormously on how reliable you demand the agent to be. At a 50% success rate, where it finishes the whole job half the time and fails the other half, the horizon is some length. But METR measured that when you ask for 80%, still failing one task in 5, that horizon collapses to about a quarter to a fifth of it. Demand more still, and it shrinks further. The task an agent can do reliably is a small fraction of the task it can pull off once in a while, and that gap is the whole story. So no, you cannot simply wait for a smarter model to rescue you. For any given model, that reliable horizon is a hard ceiling, and pushing it outward takes ever harder gains in the reliability of every single step. So you cannot outsmart compounding. You have to engineer around it. And here is the genuinely beautiful part. Building something reliable out of unreliable parts is not a new problem. It is one of the oldest problems in computer science, and we have known how to solve it for almost 70 years. Back in 1956, John von Neumann wrote a paper whose title is basically this whole episode: How to Build a Reliable Machine Out of Unreliable Components. His answer, and the answer ever since, was never make a perfect part. It was build a smart system around imperfect parts. We did not get reliable computers by making flawless transistors. We got them with redundancy, with error-correcting codes, with checks at every stage. So here is the same idea for an agent. Move 1. Shorten the chain. Do not hand it a 50-step quest. Break the job into short pieces and check the result of each piece before moving on. Watch what that does to our dying cohort. Every check catches the errors and resets the line, so instead of decaying all the way down, the agent keeps surviving. Move 2. Do not let the model grade its own work because we just saw it cannot. Check it against something outside itself. A tool, a test, a second model with a different job. And where it matters, lean on von Neumann's own trick, redundancy. Ask more than once with different checks and take the majority, the way a critical system runs on backups instead of one perfect part. Move 3. For anything that touches the real world, deleting, sending, spending money, put a human in the loop to approve it. Notice the pattern. None of these makes the model one bit smarter. Every single one is a piece of the system you build around it. The trust was never in the part. It is in the architecture. And here is the best part. You can run this exact thing yourself, completely free on your own computer. You need 3 things and every one of them is free. First, a tool called Llama. It runs the model locally and it installs in a single click on Mac, on Windows, or on Linux from llama.com. Second, the model itself. One command, llama pull qn3, and it downloads straight to your machine. and third, Python, which your computer most likely already has. The little script I am about to run is up on GitHub. The link is right there in the description below this video. Download it, run it, and watch your own local model do exactly what we are about to see. Let us watch this happen for real on your own computer. I gave our local model QN3 a genuine multi-step task. Take 5 subscriptions, work out the days until each one renews, and add them all up. First, one step on its own. It gets it right almost every time, nearly perfect. But now the full 5-part task run over and over, and it succeeds only about half the time. One step alone is nearly flawless, yet chain 5 together and half of them fall apart. That is the exact collapse we drew, now real on your own machine. Each step is easy, but the long task breaks because the model quietly drops a step here and there and never notices. Then I add one thing, a check in my code that counts whether it really handled all 5 before it is allowed to answer. Same model, same task, and the success rate jumps to around 9 in 10. We did not change the model at all. We changed the system around it. So here is the real shape of it. Every step is a little bit fallible. A long task multiplies those little odds together, while the growing context quietly makes each step weaker, and the agent has no way to feel itself going wrong. That is why a whole string of reasonable-looking steps can still end up somewhere you cannot trust. The fix is never just a smarter model. It is a smarter system. Shorter chains, a check on every step, and a human at the controls for anything that really matters. Which leaves one honest truth to sit with. Today, a long, fully autonomous agent, the kind that quietly does your entire job while you sleep, is not something you can trust yet, and now you know exactly why. But a tight, well-checked agent with a person in the loop you can build right now, and it is genuinely powerful. There is one piece left. So far, every tool we have handed our agent we wired up by hand with custom code. Next time, we will see the one standard that lets any AI plug into any tool without rebuilding that glue every single time. That is MCP, and it is where we go next.